Okay, so today I want to talk about, last time was mostly just one big example of the Cantor set and some related things, which are a little far out. I want to talk about another kind of major concept for just sets of numbers. We talked about open sets and closed sets so far. Today, the big topic, and probably for next time also, is something called compact sets. Compact sets. This is something related to closed sets, I suppose. It is a fact that every compact set is closed, so it's a special type of compact set. It turns out a lot of the things that we've discussed so far in the course about intervals in particular, a lot of things that we've talked about for closed intervals actually are true more generally for compact sets. For example, in the nested interval property, we used closed intervals, right? In fact, they were bounded closed intervals. This isn't something we made a big deal out of, but if you allow the intervals to be unbounded, even if they're like closed on one end, but they go up to infinity, they do not have the nested interval property, because if you started with, say, ones like this, and they go out to infinity, but you just let the left endpoint continue to go out to the right also as you go, then the intersection of all these would be empty. There's no point in all of them. If we just took, for instance, the intersection of the numbers from n up to infinity, this is empty. So this does not have the nested interval property. Remember, the nested interval property means the intersection is always not the empty set. Nested interval property requires bounded closed intervals. But I would like to consider, do they really have to be intervals? Or could they be, I don't know, some other set which is a little stranger, but they're still nested and they're still something. But like, what is required in order for you to get the nested interval property? Do they really have to be intervals? It turns out they do not have to be intervals. I don't know if we're going to get this far today, but certainly by tomorrow we will. So I'm going to say, actually, they don't need to be intervals. In fact, they need to be compact sets. So this is the concept that we're going to talk about today. Actually, they don't need to be intervals. They only need to be compact sets. So you should think of a compact set as like a closed interval. It has similar properties to a closed interval, but it's a little more loose. There are some compact sets which are not closed intervals. There can be more stuff. All right. For example, the Cantor set is a compact set, even though it's not. It's definitely not an interval. Okay, let's talk about compact sets. And that's just to get you get your interest up. I don't know how up your interest is, but here's the definition of a compact set. So in our book, they always use K to denote a compact set. So K, a subset of R, is compact. Compact in ordinary language has a connotation of like small, something which is small, but that's not, a compact set doesn't have to be small at all. A compact set, K is compact when it says if you have a sequence in K, if an in K is a sequence of points in K, I'm going to say something about the convergence of this sequence. It's not necessarily true that the sequence converges, but then an has a convergent subsequence. And the limit of that sequence is in K, all right? So the sort of short form of this, or if you, the kind of slogan that I would use if someone asked me, what does compact mean? It means all sequences in K have convergent subsequences which converge to a point in K, right? That's kind of the same thing that I just wrote. All sequences have convergent subsequences, and those things that they converge to are also part of the set that you're talking about, the compact set K, all right? This is what it means to be compact. This is kind of complicated, but let's just see if we can do some examples here. So, as a first example, it is a fact that any closed interval is, any bounded closed interval, not going out to infinity, but a closed interval, let's write, say, A to B, is compact. Bounded, right? B is not infinite, and A is not negative infinity. Any bounded closed interval is compact. Why is that? We have to think about, what if you have a sequence inside a closed interval? So the picture you should have in mind is the closed interval from A to B looks like this, right? Here's A, here's B. And we are including the endpoints A and B. I'm trying to convince you that it's compact. You need to consider, if we have a sequence in here, that would be, a bunch of points. They don't necessarily, it doesn't have to be monotone. These points, they don't have to be always increasing or always decreasing, but maybe they could, I don't know. All right? So, any sequence. First of all, can you say why, do you know that I'm trying to justify that all sequences in K have convergent subsequences, and the thing they converge to is also in K. Can you say why does it have a convergent subsequence? Do we know that? Yeah, this is because of the Bolzano-Weierstrass theorem, immortalized in the rap by Steve Solon, that if you have a sequence in a closed interval, a bounded closed interval, then it has to have a convergent subsequence. So any sequence in AB has a convergent subsequence. This is by the Bolzano-Weierstrass theorem. BWT. All right. And so that's part of the definition of compact. Compact says any sequence has a convergent subsequence, and the thing that it converges to is actually in the closed interval. So there is a subsequence which actually converges. So maybe it looks like this, say. And how do you know that the limit of that sequence is actually in the closed interval A to B? It doesn't leave the closed interval A to B. That's because the closed interval A to B is a closed set. And so it means that if there is a limit, then it must be in the set, because a closed set contains all of its limit points. All right. So any sequence has a convergent subsequence. That's the Bolzano-Weierstrass theorem. And then the limit point of that sequence must be in K. I meant the closed interval A to B, because A to B, the interval A to B is a closed set. And therefore, it includes all of its limit points. All right. And then these two things together means that it is compact. So the interval A to B is compact. Those are the two parts of the definition, right? Any sequence has a convergent subsequence, and the limit of that sequence is in the set, right? So this is why a closed interval, bounded closed interval, is compact, all right? Actually, what all these things that I said here, it's not so important that it's an interval, right? In fact, so I'm going to say actually, any bounded closed set is compact. Because the fact that it's bounded means you can use the Bolzano-Weierstrass to get the first part there, and the fact that it's a closed set gives you the second part there. So exactly the same argument. If you break it down into these two steps, it doesn't have to be an interval. Any closed bounded set is automatically compact. The fact that it's bounded means you can use the Bolzano-Weierstrass to get the first part, and the fact that it's closed means that you can get the second part. All right. So any bounded closed set is compact. What about things which are not compact? By the way, can I just say, for example, the Cantor set. The Cantor set is bounded because it's between 0 and 1. And it's also closed. That's less obvious, but we did talk about that fact last time. The Cantor set is a closed set. So the Cantor set is an example of a compact set, which is definitely not an interval. It's a very weird set, but it is compact. All right? Okay, what about something which is not compact? What about an interval which is not bounded? So something like the unbounded interval from 0 to infinity. This is not compact. The closed unbounded interval from 0 to infinity. It is not compact. Remember, compact means every sequence has a convergent subsequence whose limit is also in there. Can anyone give me an example here? Not compact means you can find a sequence which does not have a convergent subsequence, or perhaps a sequence which whose limit is outside of the set. Not compact since. Can anyone think of a sequence in this set which does not converge, or which has no converging subsequence? Or something which does converge, but the limit point is outside of the set? Yeah. Something like an equals n. This sequence, this does not converge, and in fact, no subsequence of this converges, right? So this has no convergent subsequence. And so that means this is not compact. And I should just say, and it is, an is in this interval every time, right? So that means the set, 0 to infinity, not compact. Great. For exactly the same reason, can I say also, say, all of R is also not compact. The same example works, right? All of R is not compact. Also, something like n. Also, the same example works. The same sequence here has no converging subsequence. Also, Q, which is a much weirder set, but it's still, the same example still works for Q, because all those things over there are in Q. Just 1, 2, 3, up to n, right? These are all examples of non-compact sets. How about, here's a different one. Another one of our favorite sets, the set of 1 over n, where n is a natural number. Is this compact? This one's different because it's bounded, right? Is it compact? You got to think, can you find a sequence? Remember, compact means all sequences have convergent subsequences, and the thing they converge to is in the set. Can you think of a sequence in here which either has no converging subsequence, or maybe it does converge to something, but that thing is not part of the set? What do you think?
Yep.
Yeah, you can make a sequence in here which converges to 0, but 0 is not part of the set. So here, this is also not compact. Since there is a sequence, in fact, you just use this as the sequence, right? Since this sequence, an equals 1 over n, it is in the set, like all those terms are in the set, but the limit is outside the set. And compact means that all the sequences, their limits have to be in the set. So here we have a sequence which is in the set, but its limit is not in the set. All right, so that is another example of a set which is not compact. How about one more example? What about the open interval, say 0 to 1, like that? This is the open interval from 0 to 1. What do you think? Compact or not? You got to think about, can you find a sequence in here which has a limit, but the limit is not in here? Yeah, what do you think? What should the sequence look like? Yeah, that same sequence will work in this set also. All right, so this one also not compact, since the same sequence will work, right? The sequence 1 over n, these terms are in the interval 0 to 1, but the limit is 0, which is not in the interval 0 to 1, right? Anything that looks like an open interval, you can always find a sequence of points that are like marching up to the endpoint, but the endpoint is missing, and so it won't be in the set anymore. So actually, it's not so hard to show. Any open interval is not a compact set for this reason. All right. How about this? Something just like 1, 2, 3. Is it compact or not? You got to think, if you take any sequence just using these 3 numbers, does it have a convergent subsequence, first of all? And then secondly, the thing that it converges to, is it also one of these 3 numbers? I think the answer is yes. So this one is compact. If you have a sequence in here, first of all, it does have a convergent subsequence because of the Bolzano-Weierstrass, because this is bounded. And so there is a convergent subsequence. But for these 3 numbers, if it converges, the subsequence converges, that means it must just be always 1, 1, 1, 1, 1, or 2, 2, 2. It can't jump back and forth because then it won't converge. And so then what it converges to is just 1 or 2 or 3. So it can't converge to any other number than these 3 numbers. So this one is compact. All right. I would like to talk about. So I would say, like, when I think about compact sets, sort of like in my heart, my informal view of what a compact set is to me. This is like if I was trying to win the 3rd grade essay contest of what a compact set means to me. I would say non-compact. In my head, I would think of this as me. Non-compact is like first of all, if it stretches out to infinity, then it's automatically not compact. Stretches out to infinity or minus infinity, right? Or a case like this, an open interval, a case in which it is missing some of its limiting points, where you can find a sequence which marches up to the edge, but the edge is not there. So non-compact is like if it stretches out to infinity, or if it lacks some limiting points that should be in there. Like the open interval, I would say it's missing those endpoints. So you have a sequence going up to the end. The endpoint is gone, and that's what makes it not compact. This is very informal, but this is how I think about, how I feel about compact sets, right? Or non-compact. Okay. What I want to talk about, the big sort of theorem for today about compact sets is we already proved half of this. So this is, the book refers to this as something like the characterization of compact sets or something. It doesn't really have a name. It just says a set K in the real numbers is compact if and only if K is closed and bounded. All right, a compact set, the set is compact, is equivalent to saying that it is closed and bounded. Still recording the sound here? I just had a great idea for the folks back home. I can just listen to myself recording the sound and write everything later on today. It'll be a fun little activity for me. All right, this is if and only if compact, if and only if it's closed and bounded. Now, we already said something to this effect. We said that if it's closed and bounded, then it is compact. All right, so that's half of this proof. Any closed and bounded set is compact. We already said that. So that was this way. All right, this is already done. I did that back when my screen was working. All right, if it's closed and bounded, then it is compact. The other way around is what I'm going to talk about now. So you assume that set is compact. We need to show that it is closed and also bounded. So let's try that. So I'm going to say let K be compact. And I want to show that K is closed and bounded. And these are, two different things, so we're just going to do them separately. Closed and bounded. All right. Let's do bounded first. I think bounded is what I'm going to do first. Yeah. Remember what compact means? I will just remind ourselves. Compact here means that if AN is in K, if you have a sequence in K, then a subsequence converges to a point of K, right? This is what we're going to use when we use the fact that K is compact. It means you have a sequence in K, then some subsequence converges to another point of K. Okay, let's do bounded first. That's what I said I wanted to do. For this, I'm going to do a contradiction, although the idea behind this half of the proof is really not difficult at all. Imagine, what if K was not bounded? That means K somehow stretches out to the right forever, or maybe to the left forever. It doesn't necessarily need to look like an interval, but it does have points that go out to the right further. Then I think that means it automatically cannot be compact, because you could choose a sequence which goes out to the right forever, and that has no converging subsequence. So bounded, I'm going to say, to get a contradiction, we assume K is not bounded. But then, because of what I said, if K is not bounded, that means you can find a sequence in K which is also unbounded, a sequence of points in K which is unbounded. So, assume K is unbounded, then we can find, just by choosing individual points, we can find a sequence, AN in K, which is unbounded. This is going to contradict some business over here. What exactly is the contradiction with the fact that K is compact? K is compact means for every sequence, there's a converging subsequence, and it converges to some point of K. What's the problem with that if we find a sequence which is unbounded? In fact, we can do even better. Unbounded, and how about increasing? Right? Like our sequence can start somewhere and then just keep on going up forever, right? Where's the violation then from the? Yeah, then it won't converge, and in fact, no subsequence can possibly converge for an increasing unbounded sequence, right? The sequence itself does not converge, and no subsequence of that can possibly converge. So we can find a subsequence which is unbounded and increasing, and so this means no subsequence will converge. And so K is not compact. And that's a contradiction with, our main assumption is that K is compact. All right. Okay, so this is the bounded step. Any compact set must be bounded, because if not, then you can find a sequence going out to infinity, but that will not have a convergent subsequence. And what about closed? That's the other thing. Closed. I think closed actually is a little bit easier. Closed. Remember, the definition of closed means that the set contains all of its limit points. So to demonstrate that it's closed, I have to say something like, let X be a limit point. Okay. And what I want to show is that X is in K, right? Closed means that every limit point is an element of the set. And so to show it's closed, I choose any limit point, and I have to show that that point is part of my set. Okay. So the idea here is, I have K is some set like this, and a limit point, maybe it's right on the edge, maybe it's on the inside already, but this is my X. Can we show that X is actually in K? Well, the fact that this is a limit point means there is a sequence which leads up to X. But then because it's compact, like I said, a compact means that when you have these sequences, the thing they converge to is actually part of the compact set. So that's the idea of what I'm going to write here. Since X is a limit point, there's a sequence in K which leads up to X, or which converges to X. Since X is a limit point, there exists a sequence, I'll call it Xn in K, with Xn converging to X, right? That's what it means to be a limit point. But that was a theorem we had about limit points. The definition of limit point was slightly different, but we showed that something is a limit point if and only if there are sequences of points which lead up to it. All right, since X is a limit point, there is a sequence which converges to X. And then because of the compactness, remember part of the definition of compactness means these sequences, they converge, and what they converge to is also in K. And so I'll say since K is compact, this means X is in K. Right? Sequence converges to X. Compact means that the limits of the sequences are also in the set. And that's what I wanted to show, right? I said I want to show X is in K. So that's it. All right. Compact set is, a set is compact if and only if it's closed and bounded. That's what we just demonstrated. So another way, I went through all of those examples. Another way you could check if an example is compact or not is just ask yourself, is it closed and bounded? And a lot of those you can tell immediately are not. Like, for instance, R is not bounded, and so it's not compact, right? N is not bounded. Q is not bounded, so these are not compact. There's also this set with the 1 over n thing. This is bounded, but it's not a closed set. I don't know if that's easy for you to think about, but it's not a closed set because it doesn't include the endpoint. Or something like an open interval. It's not a closed set, so it's not compact. These are all not compact. Once you know this theorem about closed and bounded, it becomes a little easier to tell if I present to you a set whether it's compact or not. The Cantor set is closed and bounded, so it is compact. All right. Excellent. So the last thing I want to talk about, I guess we did get to it. I want to talk about the nested interval property for compact sets. Now I'm not going to call it the nested interval property anymore because it's not about intervals. It's about any compact set. So let's talk about the nested, I think the book calls this the nested compact sets property, something like that. I don't know if they have a name for it. I'll just write it as a theorem. This is the nested interval property for compact sets. All right. It's going to say if we have a bunch of compact sets, so I'm going to say let, say Kn all be compact sets. There are many of them, and they are nested, which means K1 is the biggest, K2 is a subset of that, K3 is a subset of that, etc. All right? These are nested compact sets. The nesting is all those subsets. And then, what does the conclusion say? The nested interval property says the intersection of all these things must be not empty. And that's what the conclusion here will say. Intersection n equals 1 to infinity. Kn is not the empty set. All right. So the picture you should have in your minds here is just like the nested interval property, although these things, they may not be intervals. They might look slightly different, although they're still going to be closed and bounded sets. Although they could be very weird, like the Cantor sets. The picture that I have in my mind, though, is something like K1 is a big compact set. Maybe it has a part which looks like a closed interval. Whatever it is that I'm drawing here has to be closed and bounded. Maybe it has a few like individual points, because that is okay in a closed set. And then maybe it has these guys also. So here's a picture of maybe what K1 might look like. This is a compact set made up of 3 separate closed intervals plus 3 extra points. All right. That's K1. K2 should be a smaller compact set. So maybe it has, like, this part of it has been shrunk down a little, and this part maybe is the same. Maybe it only uses 2 of those points, and maybe right here, instead of that, it does some weird kind of like 1 over n type thing where the points all converge to this one on the left. All right, 1 over n but it does include the n point. That's what makes it compact. All right, maybe this is K2. All right, the nesting means just that this one is a subset of that one. All right, they don't necessarily have to look like the same sort of funnel type shape, because weirder things can happen. All right, maybe K3 is just that one. All right, it's a subset of the previous ones. Okay, this is how the picture in your mind should look. You should feel like it's kind of like the nested intervals picture, only the sets can be a little weirder. They're not necessarily intervals. All right. Now, how are we going to find a point in the intersection? You have to say, when I take the intersection of all of these, there is some point going to be left over. In the case of the nested intervals, you look at the endpoints and you take like the soup of all the left endpoints or the inf of all the right endpoints. That was the idea for the nested intervals. It's a little harder to do something like that here. But the idea is I'm going to just choose some points. So I'm going to choose just any point, really, xn in kn for each n. I'm building a sequence by just choosing one point at each level here, all right? Now, I was going to use my fancy colors on the fancy screen, but I can't no more. I'll put, how about I'll use like a little star here. Let's say that's x1. This is the chosen point in K1, all right? And then I have to choose a point in K2. Maybe I'll choose this one right here as x2. And then x3 has to be some point of K3. I'll choose it right there, maybe. x3, right? And so on. That makes a sequence of points in, well, what does it make a sequence of? I suppose this would be a sequence in K1, because all these ones down here, they are automatically part of K1, right? If xn is in Kn and the nesting works in this way, all of these points will already have been in K1. They have to be, if they're in the lower down sets, they must also be on the top set. So all of these are in this first set, K1, because of the nesting. Each one might not be in the sets below, but it must be in all the sets above because of the way the nesting works. All right. So that means that the sequence xn as a sequence, it is, all of those points are elements of K1. That's what I just said. And because K1 is compact, what does that mean? It means there is a subsequence which converges, and the limit of that subsequence is in K1. All right? So this is in K1. Since K1 is compact, remember, compact means any sequence in the set must have a convergent subsequence, and the limit must also be in the set. So since K1 is compact, there is a convergent subsequence, and its limit is, I'll call it x, and x must be in K1, right? Because K1 is compact and the sequence is in K1, compactness means that it converges, a subsequence converges, and the limit is also in K1. Okay? So whatever these things do, these things, there's a subsequence of those points which converge to some point which is in K1. I will have you notice, check it out. What if I look at this sequence, but I start looking only at x2, not starting from the first point, but just starting from the second point? Well, it's still the same sequence, so it still has a subsequence which converges to x. So if we consider only x2, x3, x4, etc., just ignore the first point, but look at all the other ones. It's the same sequence, so it still has the same converging subsequence, and it still converges to x. So if we consider only these, they still have a subsequence converging to x. This same limit point x, right? But this time, since I ignored the first one, actually all of these are now in this set K2. They're all in the second set, right? And so the limit of them must be in K2. So they still have a subsequence converging to x. So x must be in the second set, K2. This is since all terms x2, x3, etc. are in K2. And K2 is compact. So whatever they converge to has to be in K2. So this limit point x, it is in the first set. It's also in the second set. Would you say it's also in the third set? It is. You just say the same step. So instead of ignoring the first point, you ignore the first 2 points. Then this thing must also be in the third set. All right. So I'm going to say for the same reason, that is, consider only starting with x3, then x4. In that case, the same reasoning would tell you that the limit point x is in K3. So for the same reason, the limit point x is in K3. See that? I'm going with this? You can do this for this by the same reason. X is in all of them, right? It's also in K4. It's also in K5. It's in all of them. So this is the end of what I'm going to say. Let me just squeeze it in right here. So for the same reason, X is in K4, X is in K5, etc. Really, X is in Kn for all n. And this is the end of what we needed to show. Remember, the whole proof was supposed to show that the intersection is not empty. If X is in Kn for all n, that means X is in the intersection of all the Kn, n equal 1 to infinity. And this is what the whole point of this theorem is to show that the intersection is not empty. But there it is. There is a point in the intersection. So the intersection of the Kn is not empty. That's all there is to it. The nested compact sets property. Right? This actually is another sort of easy, I don't know, once you know this theorem, it's an easy way to justify the fact that the Cantor set actually contains points. Remember, the Cantor set involves removing points in different stages. But every stage of that procedure was a compact set, which means when you take the intersection of all of them, there must be things left in the intersection. All right. I think we have a few more minutes, but I think I'm going to leave it at that. We only have 3 minutes. Because my arm's tired.